Yeah, hello Abhinav. So I'm gonna introduce our next speaker, who is Abhinav Valada. He's an assistant professor at the University of Freiburg, where he's the director of the Robotic Learning Lab. Abhinav received his PhD from University of Freiburg and a Master of Science in Robotics from Carnegie Mellon University. Abhinav is an Alice Scholar, a DFG Emulator AI Fellow, and a co-chair of the technical community on robot learning of the IEEE Robotics and Automation Society. So Abhinav, we are looking very much forward to your talk. The stage is yours.
Thank you for that kind introduction, and thanks also for inviting me. So today I'm going to talk a little bit about scene understanding to SLAM, so everything from perception to localization, and in the context of automated driving, but also more general in context of autonomous systems, any kinds of robots. So let's see, if you look at the typical autonomy stack or automation driving stack, we have this modular structure going from perception to action in the end. And if we see in the last decade, we've had tremendous improvement in performance for many of these tasks. I think most of this is in the perception domain, but we've also seen this trickle down to prediction and robotics. We've also seen this in control. But if we see where this is going, this has also increased the dependency in manually annotated labels or reward functions if you're doing reinforcement learning, and both of these are environment as well as domain specific. And if we see where state-of-the-art models are going, I mean, the state-of-the-art models lack efficiency in both computational complexity and inference time, and most of our autonomous systems have very limited resource computational budgets, and it's intractable to deploy these systems in real-world situations. And another factor is that these learned models are only reliable in limited scenarios, and they do not often generalize to diverse domains or locations, and even seasons and so on. But we need these autonomous systems to be extremely reliable in these challenging conditions. And if we generalize this into a little bit more in terms of all autonomous systems, we've seen that we have many types of robots. These could be like leg robots or self-driving vehicles, or maybe in a few years even home-assisted robots. And even though all of these systems have kind of the same autonomy stack, but these transferring these learned models across different embodiments is almost infeasible nowadays. So this brings us to the question that how do we create basically, how do we make robots learn these perception and localization models that scale across different tasks, modalities, embodiments, and so on. So let's first look at this on the level of perception, and then we will also talk about how this affects localization. So first, these autonomous systems have multiple sensors around them, as all of us know. They have LiDARs, thermal cameras, color cameras, event cameras, and so on. And from this, we want to perceive the elements of the scene around them. And the good thing about LiDARs is that they have this really rich illumination-independent geometric description of the scene, and they are basically not affected by these environmental changes that we see with cameras, right? And but there are many caveats in using this. So one of the main things is that the irregular sparsity of point clouds make employing conventional CNNs that will do well in the image domain for in the LiDAR domain. And you can see that okay, we can use 3D convolutional operations, but these are intensive memory operations, and this makes them unsuitable for real-time applications. And this led us to proposing a new form of convolutions that operate on range images, and we call this the proximity convolution module. So the standard 2D convolution is very limited in its geometric modeling capacity because of this fixed grid structure that we do the sampling. And to tackle this, we proposed our proximity convolution here. So this basically exploits the range information to then sample the spatial sampling location. So you see on the bottom here, I'm not sure if you can see the mouse. Based on the range information, we then sample the locations that we want to do the convolution on. And this enables us to capture really rich semantic information that's there, as well as geometric information here. And we also proposed another variant of this that we call as distance-dependent semantic, that we call as range-guided, depth-wise acrospatial convolutions. And essentially what we do here is that we take acrospatial convolutions and we change the dilation rate of the convolutions based on the range values that you see in the image. So what we do is that we do more denser sampling in further away objects where we have sparse points, and we do more sparser sampling objects that are near because we already have dense points. And we employ this, you can employ this at various stages of the network. So we proposed an architecture that we call efficient LPS to do Panoptic segmentation, and some very quick results. On the left, you can see the model doing Panoptic segmentation. So here we want to identify the semantics as well as the instance labels of objects. One thing that you might note here is that when you have these dynamic objects, such as cars that are parked on the sides of the road, you'll notice that they have these mixed colors. This is because in regular Panoptic segmentation, we don't do any aggregation across the temporal dimension. And most dynamic objects are handled downstream in the pipeline by tracking, so this is solved in a different way. But when we started thinking about this, that are there any actual benefits in learning these two tasks together? So learning the semantics as well as the propagation of the semantics across time, so instances across time. So then we formulated a new task that we call as panoptic tracking. People have also called this video panoptic segmentation subsequently after, and we proposed an approach to do this simultaneously learning the panoptic information, but also tracking them object-wise. And that's why on the right side, you can see that the instances that we have are very accurately tracked. Okay, so we saw some really good results, but the caveat is that these models really work, on where you pretty much have lots of label data that you have trained them on. So if you deploy these systems in environments that are substantially different, you'll notice that they don't work really well. And I think another specific characteristic when it comes to LiDARs is that when you deploy them on a different car or different robot, which has a different type of LiDAR, these don't tend to work well. So to solve this problem, we basically proposed a completely unsupervised domain adaptation approach. And the goal here is to adapt a model that is trained with supervised data to a new domain with a new LiDAR. This can be a different number of scan lines, different intensity patterns, as well as different environment as well. So here we decompose this problem into two. One is called data-based domain adaptation and the other model-based domain adaptation. And in data-based domain adaptation, our goal is to basically reduce the domain gap by processing the raw LiDAR scans to resemble the scans that were basically used by while training in the target domain. So that's what you see on the left side here, but we also match the intensity distributions. And on the right side, we see the model-based technique that we have. This basically reduces the domain gap in the feature representations that are in the both domains. And some very quick results, you can see basically a model that's trained on Semantic Kitty, which I think has 64 beams, and on the right on new scenes, which has 32, and it's much sparser. So on the left you see without any domain adaptation, sorry, and on the right after the domain adaptation, and we can see quite good results in learning this completely in an unsupervised manner. Okay, so we saw, in addition to just frontal view panoptic segmentation using LiDARs, HD maps have also become quite essential in the automotive domain, and they primarily are useful because, as we all know, they help several downstream tasks such as planning. So we wanted to tackle this. Can we generate these HD maps in an online manner as we get camera data? And we wanted to push this even more to the limits, assume that we only have one monocular camera now on your car or your robot that's looking ahead of the scene, but we want to generate the panoptic maps from the top view. So that's our goal here. And to tackle this, we proposed the first approach to do this, actually, that we call as Panoptic BEV. And our approach, in short, consists of an encoder, a dense transformer module that transforms the image features to top view features, and then we have, as usual, a semantic head and an instance head, which then gives us a predictions for the instance segmentation and the semantic segmentation. So the main novelty here is that we propose a dense transformer that basically works on the principle of how different regions in the 3D world are projected to the 2D images. So here we have a column belonging to a flat region in the real world that projects onto a perspectively distorted area in the bird's eye view, whereas, let's say, structures such as buildings, which are more vertical, follow this orthographic projection and to a volumetric region in the bird's eye view space. So to do this, we propose a dense transformer which basically handles these two types of different objects independently. And here we basically model the vertical regions by expanding it with a 2D encoder features, and then we learn a 3D volumetric grid using 3D convolution features. And then just for flat regions, we use IPM with an error correction module. And you can see some very quick results on the KIDDI data set here. On the left, the input image, and then the predicted maps, as well as the occlusion regions that we can see. All right, so going to the autonomous driving stack, autonomous systems also need to know where they are in the environment, and there are multiple ways that we can do this. So I would say that loop closure detection in SLAM is a very essential component in making this accurate. And here we wanted to basically learn this task of loop closure detection by identifying whether you have visited this place or not. So then, as we all know, after that a loop is found, then we can correct the map and the accumulated drift accordingly. So over the past years, there's been a lot of deep learning approaches that have been proposed to address this loop closure detection task. And when we started working on this, one of the things that we noticed is that all the existing approaches perform really poorly in reverse loops, which means that it's opposite to the direction that you have trying to match the point clouds that you have. And this is pretty much across the entire spectrum. And we did very extensive study basically showing that most of the data sets only have loops that are in the same direction. And this is why people didn't really notice this, that they don't perform actually very badly in reverse loops. So we specifically addressed this task in our paper this year that's published on transactions in robotics, where we introduced an architecture that we call as LCD-net. And this effectively basically detects loop closures in LiDAR point clouds. So in brief, so our LCD-net simultaneously identifies previously visited places, but it also estimates the 6DOF relative transformation between the scan and the map. So our network here is composed of a shared feature extractor for which we use standard off-the-shelf PVR-CNN, and then we have a place recognition head and relative pose estimation head. So then the feature extractor generates a set of n rotation and translation invariant key point features, which are then shared between the place recognition and the relative pose estimation heads. And the place recognition head then generates a global descriptor for the point cloud, which we then use to decide whether the 2 point clouds are the same place or not. Finally, the relative pose head estimates the 6-degree of freedom transformation that's used to align the 2 point clouds. Okay, so in our LCD net, the place recognition head, we leverage net MLAD layer to aggregate a set of key point features that are then obtained by feature extractor. And so for this, we use the triplet technique where we consider a positive and a negative sample with respect to the query. So here the positive sample is the point cloud from the same place, and the query is basically, and the negative sample is the point cloud from a different place. And then we use the triplet loss to enforce the distance between the two descriptors to be as small as possible. So then we have a relative pose estimation head. So here each key point in the source point cloud is then soft assigned to one or more key points in the target point cloud. And we use a recent extension of the SYNCHRON algorithm to solve the unbalanced optimal transport problem for this case. And based on these correspondences, we estimate the 6 degree of freedom. And here our relative pose estimation head is completely fully differentiable. And during inference, we then replace the relative pose head with basically ransack. And this exploits the features that are extracted by our network and makes them more generalizable. So we evaluated this on 2 standard data sets, Kitty 360, as well as our in-house data set that we collected in Freiburg, and we compared this with both state-of-the-art handcrafted approaches as well as deep networks. And as we can see here, our network basically outperforms pretty much all the methods that are learned as well as handcrafted on both of these standard benchmarks, but we can see also compared to in an unknown environment like that we collected in Freiburg, we also achieve quite good performance. So we integrate this into an existing SLAM system, LeoSAM, and we have made this publicly available. So here you can see some online results on the Kitty data set here. And here the noisy odometry that we get eventually makes the trajectory drift significantly skewed compared to the ground truth, as you can see here. But every time a loop is detected, then the trajectory and the map are then reduced to reduce the drift. And here we can see that our network is effectively able to detect slips even when we have very strong drifts, as you can see here. Okay, so we further exploit this very recently, and most loop closure detection methods, as we saw before, only use this geometric information. So we started thinking, but we also have this very rich semantics that we can learn from the scene. So in this work, we wanted to further exploit the semantic information for loop closure detection, for more than that panoptic information. So we extended our previous LCD-net approach to a new approach that we call as padlock. And here we want to do, again, LiDAR-based loop closure detection and registration using a 3D convolutional feature extractor backbone, and again, a global descriptor head similar to LCD-net, but that I just presented. And then here, the novel thing is that we propose a new transformer-based head for point cloud matching and registration. And this uses the panoptic information. So a transformer here consists of queries, which we use the features of the source point cloud, and keys, we use the features of the target point cloud. And for values, we sample points from the target point cloud. Fortunately, I don't have too much time to go into this right now. So here we also propose multiple methods for estimating the point-wise matching confidence between the diversity of the indices, and also improve the forward-backward consistency. We proposed 2 shared matching and registration heads, with the source and target's input swapped by exploiting the relative transformation such that they should be inverse of each other. And as I said before, we also exploit panoptic information. So we assume that while training, we only need this panoptic information. And this is then exploited in a novel loss function that reframes the matching as a classification task. And in this case, the semantic labels. And then we use the graph connectivity assignment for the instance labels. And we only need this while training because we only use this in the loss function. So again, we evaluated it in all the data sets as we did in our LCDNet, and we achieved substantially lesser false positives compared to our previous approach. And we also achieved state-of-the-art performance for point cloud registration compared to most existing techniques, as you can see here. All right, so we can do SLAM and we can build this really nice map. So, but in a lot of robots, I guess it may not be necessary to have always LiDAR. So this starts made us to think basically, can we use pre-existing LiDAR maps to just localize using an image? So imagine that you have a built LiDAR map and now you want to only have cameras on your car or only have a camera on your robot, but we still want to localize in these pre-existing LiDAR maps. And for this, we proposed an approach to do this that we call as CMR net. So here, the input to our approach is an existing LiDAR map, that environment, an RGB image from a camera that's mounted on a vehicle, and a very rough localization estimate, let's say, for example, using GPS. And one important thing to note that is to be as general as possible. We use maps with only geometric information without any color or intensity information. Okay, so how does this work? So we have the LiDAR map, the environment, and we have the real pose of the camera and the initial rough position estimate. So what we want to do is find the transformation between these two poses. And an ideal way to do this is to synthesize a depth image by projecting it onto the map into the virtual image plane at the given pose. But if we try to do this and we visually compare, we can see that because this rough initial pose is not very accurate, we get this really misaligned image as we see here. And here we see that with an example that these two don't align. So instead, if we try to compare the map projected onto the ground truth position, you see that they are very well aligned. So here we combine this in our CMRNet++ using a deep learning approach with standard geometric techniques to make the localization as agnostic as possible to the type of camera parameters such as intrinsics and so on. And we want to do this because we want to generalize to unseen cameras as well as unseen environments. And then we do this by removing the metric reasoning outside of the learning process. So we decouple the localization into two, pixel to point matching step, followed then by a pose regression step. So in the first step, the CNN here only focuses on matching at the pixel level instead of doing the metric basis. And this makes it independent of the intrinsic parameters of the camera. And the parameters are instead employed in the second step, where we use traditional vision methods to estimate the pose of the camera, given the matches that we get from the first step. So we evaluated this on three very different diverse data sets, Kitty Argoverse, Lift, and as you can see, this contains images of very different resolutions, and they are also collected in diverse environments. And here we want to train on a data set that contains Kitty and Argoverse combined, and then we evaluate on an unseen city on Lift level 5, which is completely different city, completely different camera resolution, as well as different sensor properties. So let's see some results on the Kitty data set. So here you see the map projected with the initial rough position estimate, and you see that because the rough position estimate is not very accurate, that this keeps very jumping around. Whereas if you use the ground truth pose, of course, we get very aligned maps. So Then you can see our predicted the predicted localization pores from our CMR-Net++, and we can see that our network is able to perform this post-regression quite accurately. So these are some initial results from about a year ago. We have a much improved version, which is still under review. So at that time, we could achieve a median error of 0.1 meters in translation and 0.4 meters in rotation. And now we have reduced this to about a half. Okay, so the last thing I really want to quickly talk about is that autonomous systems or robots operate in the real world also encounter very diverse environments. And these domain gaps can pose a significant challenge for SLAM systems here. And we have seen over the years that learning-based SLAM methods are known to generalize very, very poorly to environments that are unseen, and this generally hinders the adoption of these systems. And this is because the number of environments, if we think about it, our car or our robot can encounter can potentially be infinite. And we also want to visit previously known environments. So if we consider this problem as a general lifelong SLAM approach, then we only consider this across one specific type of environment, but across long periods of time. And then we have another task called domain adaptation, which deals with this forward transfer across diverse domains, one after the other. But in this case, we don't try to remember the knowledge that we have learned in the previous domains. So we here propose a new sort of framework that we call as continual SLAM. So the difference between domain adaptation and lifelong SLAM is that here we also consider the knowledge transfer that we have learned in previous domains. And we also want to go back to domains that we have visited before. So we want to retain the performance on different domains. So we don't want to do this domain adaptation continually without reusing the information. So our setting here is that we want to use a learning-based visual SLAM approach, and we want to do this in a completely unsupervised manner. And we want to then deploy it to, again, a previously visited place after a series of domain adaptation. So here we propose an approach that we call as CL SLAM or continual learning SLAM. And briefly, it contains a dual network architecture that consists of an expert that produces basically online odometry estimates. And then we have the generalizer on the left that focuses on the long-term learning across different environments. And we train both of these in a sub-supervised manner. And then the weights of the expert are then updated based on online data, and the weights of the generalizer are updated based on both the online stream as well as the replay buffer, which contains information from the previously visited environments. And then we use the VO estimates to construct a post graph, and to reduce the drift, we also detect global loop closures and add them to our graph, which is then optimized. Finally, we can also build like dense 3D maps from the depth, which is predicted by the expert, and the optimized path. So very quickly, some results here. Here we see B fixed in yellow. Here we consider that there is no adaptation. So it's just deployed in a domain that is previously not seen. And then we have our B expert here. Here we only assume that we have this continuous adaptation, but we don't reuse the knowledge that we have learned from the previous environments. And then B general is basically only the generalizer network in our approach without the expert network. And you can see that basically our CL SLAM approach compared to all of these methods gives us the most accurate output compared to the ground truth. And you can also see an example 3D map that we can build online completely in a self-supervised manner. Okay, so to summarize, we've seen today a couple of methods to basically predict coherent panoptic information using both cameras from the bird's eye view as well as LiDAR data. And we have exploited this panoptic information for detecting loops as well as for point cloud registration. And I also presented a method to then use inexpensive cameras and leverage the images to then localize in pre-existing LiDAR maps. And finally, we also saw a method to then extend this to lifelong learning using continual learning. So all of the methods in the code that I've presented today is publicly available in the link that you can see here. And with that, I would like to thank you and acknowledge my students whose work have been presented today. Thanks, and I'm happy to answer questions that you have.
Thank you very much, Abhinav, for your very nice talk. Yeah, I think we can start with questions because hands immediately raised. So, yeah, please. Yeah, I will repeat the question. So the question is about the domain adaptation between different sensors. So if it also would be possible to basically use simulated data and do the domain adaptation to a real LiDAR sensor.
Yeah, of course. I mean, here in our work, we used we only showed this with real LiDAR sensors, but with two LiDARs. But we're also doing some ongoing work in which you can generate even more different types of LiDARs with different scan patterns and different intensity distributions. And in that work, we actually show that the networks does better domain adaptation if you have more different types of LiDARs here. And in our work currently as published, we only did this with two. And this kind of intuitive also, I think, because in the image domain, we have seen this sort of augmentation that networks learn. And this is also the same case in domain adaptation using LiDARs that we see.
Okay. Yeah, maybe I can briefly ask something additional to this question. How far do you think if you would use for instance, domain adaptation from a LiDAR to a stereo camera, for instance, depth map from a stereo camera or point cloud from a stereo camera? Do you think that would be possible to go in this direction, or is the domain gap just too wide, basically?
Very, very interesting question. I guess there you tackle a very different problem, right? Like there you also, I mean, you have on one side the different number of scan lines that you get from depth image projected that you get, but then you also have this very different noise that you get from stereo images, right? Which we don't really tackle. So I think there's an additional challenge that we have to do. But what could be interesting is the other way around, right? Like not to go from stereo to LiDAR, but from LiDAR to stereo. And there, let's say that you have a LiDAR that you train your network to do a task, but then in the end you want to do that task only with a stereo camera again because it's like inexpensive in that case. I'm not sure if there's any existing works, but I definitely think that's an interesting problem. And here you could think of also exploiting basically self-supervised learning to then do the depth estimation using even monocular cameras and then do the domain adaptation, also taking into account the noise maybe that you have.
Yeah, okay, thanks. Yeah, there is another question. Maybe I ask the first one, then we do the second one, because otherwise I cannot remind. Yeah, it's about the image to LiDAR registration. So the question was how you design the features, basically, which you use. What kind of features are you using to match between the image and the LiDAR scan? And also what kind of matching techniques you in the end use?
So here we use the matching, I mean, we have a standard point network that we adapted to do the matching, and that is independent of the camera parameters, right? And then we just use PNP and ransack to estimate the 6 DOF pose.
Mm-hmm. Yes, the second question.
Thank you. The second question about the initial guess of the GPS. You said that you have initial prior for the localization. What is the, how large is the pose error? A few meters, hundreds of meters?
We considered up to 5 meters, and I think in the newest work, which is unpublished, there we consider larger errors in the post, but in the initial published work, only within 5 meters.
Are there more questions? Yeah, there's one question from Patrick.
Yes, thanks for the great talk. There's another question from the audience, from Jordan Sewell. Have you tested your LiDAR loop closure and localization method using a tilted LiDAR as well?
Good question. I would say no, because all the data sets that we tested are only, like straight, I guess. But we did experiments in our paper where we artificially translate the point clouds with various rotations. But I guess this still does not really cover the aspect of the tilted LiDAR.
Okay, thanks. I have a question myself regarding the CMR network. You've been mentioning that you need a rough initial pose for the alignment. Can you say a couple of words on like how rough it needs to be, or basically how far it can be off from the actual ground truth pose? Thanks.
Yeah, so in this work, we basically assumed that we sample while training random poses between 0 to 5 meters. And that's our rough assumption of accuracy that we need. But in some recent work that we have unpublished, hopefully to CVPR this year, that we aim to reduce this much more.
Okay, thanks a lot.
Are there more questions from the audience? If not, maybe I asked another quick one. You talked about this panoptic tracking in the very beginning. How powerful do you think is such an end-to-end approach compared to if you just do object tracking from scan to scan, basically, using Kalman filter or something? Or and solve the association problem before, basically. Yeah.
So what was the exact how beneficial it is? So yeah, I think there are basically two aspects. Sorry, I think there are basically two aspects for this. If you just compare performance, still we are not there yet that we can match the performance, of course, by filter-based methods that you want to do tracking with, right? But what the benefit that we show here is that by learning them together, you can do better transfer from each task. So in the sense that you can do this by learning tracking, you can also improve the learning semantics to make them more temporally consistent. And also the other way around, by using the semantic information or instance panoptic information, you can also do better temporal matching, right? Mm-hmm. So I think like that is really the benefit, but we're still definitely not there that we are close. But I think most approaches that have come out even after this, I've seen that. I mean, we show that it's beneficial in both cases, and if we do this independently with learning-based tracking and learning-based panoptic, then we show that it's faster. I mean, existing methods also show that it's faster and more computationally less intensive.
Okay, perfect. Thanks a lot for the answer. I think there are no more questions, so therefore, thank you very much again for your very interesting talk, for answering all the questions, and yeah, see you. Bye-bye.
Thank you very much.